Welcome. Today I'm again here with you to discuss the topic Raoult's law. Raoult's law is also our today's learning objective. So Raoult's law is very important concept of the chapter solution. Dear students, as we have studied earlier about Henry's law, this Raoult's law is a special case of the Henry's law. How it is, we will discuss it also. Yes. Now what is Raoult's law? Raoult's law is given by the scientist Raoult, so it is known as Raoult's law. And what is there in it? It gives a relationship between partial vapor pressure of a volatile component with its mole fraction. Now what is partial vapor pressure? Students, as we know, a liquid, when it is kept there in the system, in the lab or somewhere, what happens? It absorbs an energy from the surrounding and it starts converted into the gaseous state in the form of vapors. And the vapors, when we close the container, what happens? It exerts pressure on the wall of container. So that pressure is known as vapor pressure. It first gives vapors and pressure exerted by it is known as vapor pressure. That vapor pressure. Now here the term is used, partial vapor pressure. Partial means, for example, if we are having a liquid alone in a beaker, then the pressure it exerts, that is known as pressure in its pure form. And when there are mixed two components together or 3, 4 which are non-reactive, that time what pressure it will exert, that is known as partial vapor pressure. Okay. Now the concept, what is volatile component? Now volatile component is that component which will have very less boiling point. With less energy, it move into the vapor form. For example, if we compare water and acetone, acetone is having less boiling point, so less that when it fall in our body, so any part, it evaporates by absorbing that energy from our body and give us a cooling sensation. Now other substances such as sugar, salt, these are non-volatile. We are considering as here. So we will discuss what is the effect of a non-volatile component on the vapor pressure. So first let us come to what is Raoult's law. Raoult's law says that partial vapor pressure of a volatile component is directly proportional to its mole fraction in that particular solution. Okay, P for the partial vapor pressure, X is for the mole fraction. Then equation becomes P equal to P naught X, where X is the mole fraction and what is P naught? P naught is here the vapor pressure in pure form of that component, that volatile component, which we are using as a constant. To remove the constant of proportionality, this constant is used. Alright, here we will discuss this Raoult's law in the two form. First case, where we will have both the component volatile. In another case, we will see what is the vapor pressure, how the Raoult's law work when we are having a volatile component and another non-volatile. Okay, so let us first discuss for the two, both of them are volatile. According to Raoult's law, P is directly proportional to X. Component A, for component A, I will write where this partial vapor pressure directly proportional to small fraction XA, and for component B, directly proportional to XB. So P naught A XA and PB is equal to P naught B XB. Right. These are their individual vapor pressure because both are volatile. What is total vapor pressure? Partial vapor pressure P total will equal to PA plus PB. And their values are here. So we can write it becomes P naught A plus P naught A XA plus P naught B XB. This is your P total. This is our P total. Yes. And we know that P XA plus XB is equal to 1. Total mole fraction of the solution is always addition of all the components mole fraction. I can write XA is equal to 1 minus XB. So if I will write this value in this equation for XA, then it becomes P total becomes P naught A XA is value is 1 minus XB and plus P naught B XB. Multiply, I got P naught A minus P naught A XB plus P naught B XB. And from here I can write this P naught A plus P naught B minus P naught A outside will be XB. This is the final expression for the vapor pressure when both components are volatile. We can keep up to here also. Right? And next case, when we are having both the components, one of the component is non-volatile. For both being volatile, it is the addition of both components vapor pressure. So here in this case, the expression will calculate your expression. See, now here in this case, P A component is volatile, directly proportional to its mole fraction, and PA is equal to P naught A XA. And this component is non-volatile. Non-volatile has no vapor pressure. So PB is equal to 0 because it is non-volatile. So P total will here PA because PB equal to 0. This is here and P total is here P naught A XA. Right? So here the total vapor pressure of the solution will be the only vapor pressure of the component A or the component which is volatile in nature. Okay, so these are the two cases. Now question arises, why the vapor pressure decreases when a non-volatile substance or component is added in a volatile component? Yes, answer is there. Let us see. When we form the solution by adding volatile and non-volatile, now see what is the condition here on the surface. Because evaporation is a surfacial phenomenon. At surface, now see, their solute particles are also present and solvent particles are also present in the mixture surface also. Now when the vapors start moving from the volatile component, but now their non-volatile component particles also present in the wave. So these particles itself not go into the vapor state, but they also create problem for others. Right? Such are the persons also in our life, they don't want to do itself, neither want to do, right? Let others do. But we should not have work as a non-volatile. We should work as a volatile. Convert, change ourselves according to the situation to achieve our target. The same here. But problem, due to the problem created by non-volatile, for the movement of the volatile component, there is this is known as hindrance. Hindrance is there due to this vapor pressure decreases by the addition of non-volatile component. It can be understood in another way, which is given by Graham's law. It is known as Graham's law of evaporation. Yeah, what is there? According to Graham's law of evaporation, rate of evaporation is inversely proportional to the under root of density of the solution. As we know, when we will add a non-volatile component, it increases the density of the solution. Density increases, rate of evaporation decreases, right? Because it goes into the just near the solid state, so it will not come in the vapor form easily. So these are the two reasons which can be explained why non-volatile addition decreases vapor pressure. Alright, at last we will compare. I have told you that Raoult's law is the special case of Henry's law. We can see here Raoult's law directly proportional mole fraction, and here we use sign of constant is here P naught, and in case of Henry's law the same is there, partial vapor pressure directly proportional mole fraction, but constant when we use, that is KH, here we are using P naught. Vapor pressure in pure form, it is a constant given by the Henry, and if both are equal, then Raoult's law become a special case of the Henry's law. This is the concept of Raoult's law. I think the concept is clear. All the very best. Thank you.